Hello everyone, my name is Heng. I'm glad to present our ICCV paper, Dynamical Pose Estimation. We consider the following problem of primitive registration with correspondences. In this problem, xi and yi are a pair of corresponding 3D geometric primitives. T is an unknown 3D rigid transformation containing a rotation and a translation. T chronic product xi denotes the action of T on the primitive xi. And the optimization seeks to find the best rigid transformation to align the two sets of geometric primitives by minimizing the function of shortest distance between each pair of primitives. In this work, we consider 7 types of 3D geometric primitives: point, line, plane, sphere, cylinder, cone, and ellipsoid. Our first contribution is to demonstrate that the primitive registration problem can model and unify 5 important pose estimation problems in robotics and computer vision. In particular, in point cloud registration, we seek to align 2 sets of points. In primitive registration, we seek to align a set of points to a set of primitives such as lines, planes, cylinders, cones, and spheres that represent certain objects of interest. In category registration, we seek to align a set of points to a set of ellipsoids, where each ellipsoid represents the intra-class variation of a certain semantic key point. In absolute pose estimation, we seek to align a set of points to a set of 3D lines representing the so-called bearing vectors that shoot from the camera center to 2D key points. In category absolute pose estimation, we seek to align a set of ellipsoids to a set of bearing vectors. Our second contribution is to propose a meta-algorithm called DAMP that solves the 5 pose estimation problems by simulating rigid body dynamics. The core of DAMP consists of 2 insights. The first insight is geometric, where we show that given a pair of geometric primitives x and y, finding the pair of points that attains the shortest distance between x and y can be either performed in closed form or solved numerically using Newton's method. The second insight is dynamical. We consider a system of geometric primitives with rigid connections, which moves within an environment with constant damping under some external forces. Using standard results from dynamics, we can simulate the trajectory of the primitive system. Using these 2 insights, the DAMP algorithm comes out naturally. In DAMP, we treat one set of primitives as fixed, while we treat the other set of primitives as dynamic under the forces exerted by the fixed set of primitives. In particular, while an equilibrium point of the dynamical system has not been attained, DAMP first computes the shortest distance pair between each pair of corresponding primitives and spans a virtual spring between each shortest distance pair. Under the spring forces, DAMP then performs one step of forward simulation of the dynamical equations of the system. If the new state of the dynamical system is an equilibrium, then DAMP stops. Otherwise, DAMP keeps simulating the rigid body dynamics until an equilibrium is attained. To promote convergence to the globally optimal alignment, DAMP optionally uses random perturbations to escape local minima. Under this construction, we show that the potential energy of the system equals the cost function of primitive registration. Our third contribution is to prove a non-trivial and somewhat surprising result. That is, in the point cloud registration problem, DAMP is guaranteed to converge to the equilibrium point that is globally optimal for the primitive registration optimization problem. Empirically, we observe that DAMP almost always converges to the globally optimal solutions across multiple pose estimation problems. We now show some qualitative videos of DAMP. Here on the left, we show an example of point cloud registration, and on the right, we show an example of aligning a set of points to a set of lines. Here on the left, we show aligning a set of points to a set of planes, while on the right, we show aligning a set of points to a set of points, lines, and planes. This problem has been studied before, and DAMP is 10 times faster than an existing globally optimal solver based on semi-definite relaxation. Here we show DAMP aligning a set of noisy point cloud to a set of primitives containing planes, spheres, cones, and cylinders. DAMP always converges to the globally optimal solution, while there is no optimal solver for this problem in the literature. Here we show 2 examples of category level registration using the car category from Pascal 3D Plus and the car category from FG3D car. In both cases, DAMP converges to the global optimal solutions. Finally, we show DAMP performing absolute pose estimation and category level absolute pose estimation. In these cases, DAMP attains global optimality with very high probability of success. Thank you for your attention.